Hi friends, today I'm going to explain about CAN protocol, history of CAN. CAN is a controller area network invented by Robert Bosch in 1980s. CAN is a message-oriented multi-master protocol used to connect several ECUs. It is used to communicate between ECU without a host computer, and CAN follows serial asynchronous communication. Simple two-wire differential bus, and it is an already I told that it is a message oriented protocol, not a address based protocol. And identifier specifies content and priority. Lowest message identifier has highest priority because CAN follows unwired logic. So 0 is dominant here and 1 is recessive. Like zero dominant is that whenever there is a conflict in two data transmissions, then the sender who is sending zero will get the highest, will get the priority. I will explain these concepts in my upcoming slides. Then non-destructive arbitration system by CSMA. CSMA means carrier sense multiple access with collision detection. So I told CSMA is carrier sense multiple access. If the bus is ideal, then it will start transmission. Otherwise, it will wait for the bus to be ideal. That is collision avoidance. Next one, detects the it detects the collision and stops the further data transmission and initiates data retransmission. So these carrier sense multiple access and collision detection, collision avoidance is to avoid the collision between the datas, and it avoids the data corruption also. So this thing also I will explain clearly with example in the upcoming slides. I just gave basic information about carrier sense multiple access and collision detection. Then already I told that it is a multi-master and it is a broadcasting concept, and we have error detection and handling systems also here. Okay, history of CAN. So CAN was created in mid 1980s by Robert Bosch, and the design goal was to make automobiles more reliable, safer, and more fuel efficient. So Bosch used this protocol for various purposes, mainly for automotive. First thing, Bosch only used this protocol after 90s. In 19 mid 90s only other automotive companies willing to work on this CAN. So here, what is CAN? So the CAN is a ISO standard, ISO 11898. So you should know, if you are going to explain about CAN, then you have to mention the ISO standard also, and for serial communication. Now CAN is gained widespread use in industrial automations, and so many places like medical equipments where CAN is using, and it have some message types, arbitration rules for bus access, methods for fault detection and fault confinement. Everything I will explain, and you should know something about CAN. If your interviewer asking what is CAN, if you are going to attend an interview, then sure they will ask what is CAN. So you have to explain like this, that CAN is a multi-master broadcast serial bus standard for connecting electronic circuit unit, that is ECU, controller area network. It's a vehicle bus standard designed to allow microcontrollers a device to communicate with each other within a vehicle without a host computer. So there is no need to host anyone. If one node is going to send the data which has lowest priority, it is a master, then the all other nodes are going to receive the same message. If they need, all the other nodes are act like a slave. Then CAN is a message based protocol designed specifically for automotive applications, but now also used in other such areas like industrial automation and medical equipments. So the CAN bus is a serial asynchronous bus used in instrumentation applications for industries such as automobiles. Okay, in next. So in markets we have so many protocols like I2C, SPI, and UART. But why we need CAN? Because CAN protocol have more than 35 years life, and numerous CAN products and tools are also there in market, and the hardware implementation of the protocol is very easy, and we have error handling and fault confinement also. Its maximum speed is up to 1 MB megabits per second, but we can't able to work on that much. Maximum will be 500 kilobits per second. Then simple transmission medium. Only twisted pairs of wires in the standard, not like SPI, because it have four wires, like three and one chip select. But here only we have two wires, and also one wire will work. So here, and it has excellent error handling, CRC error detection, mechanism of fault confinement. Everything I will explain in my upcoming slides. I just then we have general characteristics of CAN. So already I mentioned that carrier sends multiple access with collision detection. So here every node on the network must monitor the bus that is carrier sense for a period of no activity before trying to send a message on the bus. Once the bus is ideal, every node has equal opportunity to transmit a message. If two nodes happen to transmit simultaneously, a non-destructive arbitration method is used to decide which node wins. I will see. In this diagram, we have three nodes: node 1, node 2, node 3. So, based on this concept only, the carrier sense multiple access is going to happen. So, here at start of frame, SOF, all the bits are in dominant. That means 0, 0, 0. Next, in identifier, we have 11-bit identifier, we have 1, 1, 1, 1. Next one is also 0, 0, 0, 0. And another next one is, this is one is first bit, second bit, third bit. Third bit is also recessive in all the three nodes. Then in fourth bit, we have in fourth bit we have we here the node 2 loses the arbitration here. Then after this, here the node 3 loses its arbitration here. Okay, I will explain this with an example. See, carrier sense multiple access and arbitration on message priority. So maximum you will get a question like how arbitration will follow in CAN, how arbitration works in CAN. So you have to give this answer. Two bus nodes have got a transmission request. The bus access method is CSMA bar CD plus AMP, that is carrier sense multiple access with collision detection and arbitration on message priority. According to this algorithm, both network nodes wait until the bus is free. See, both if the bus is idle until if the node 1, node 2 will wait. After this, in that case, the bus is that is carrier sense. In that case, the bus is free. Both the nodes transmit their dominant start bit. See, that is multiple access. See, node 1, node 2. if the bus is free, both the node 1 and node 2 try to transmit their messages. That is, first one is SOF, here also SOF, start of frame, and here is start of frame, both are dominant. After this, every bus node reads back bit by bit from the bus during the complete message and compares the transmitted value with the received value. See here, the thing is, here no we have node, that is ECU1, ECU2, and we have different messages. See, 1 0 1 0 1, like this. So the same thing here, they are explaining that every node reads back bit by bit from the bus during the complete message and compares the transmitted value with the received value. As long as the bits are identical from both transmitters, nothing happens. If the node 1 and node 2 behaves the same like this, means nothing will happen. Okay, the first time there was a difference, like in this example, the seventh bit of the message, the arbitration process takes place. Node A transmitted dominant level. Okay, the till sixth bit, the node A and node B both transmit the same level of bits, but in node in sorry in seventh bit, the node A transmits the dominant level and the node B transmits the recessive level. So the recessive level will be overwritten by the dominant level. So here, the already I told that lowest value has the highest priority. So the node A has the lowest value and the node B has the highest value. So this is detected by the node B because the transmitted value is not equal to the received value, that is collision detection. At this point of time, node B has lost the arbitration, stops the transmission of any further bit immediately and switches to the receive mode, because the message that has won the arbitration must possibly be processed by the node. That is arbitration on message priority. This is the thing. Carrier sense multiple access, collision detection, here carrier sense, here multiple access, here collision detection, and the final one is AMP, arbitration on message priority. So the finally it happens arbitration on message priority. So the same thing here. One more example is that 3 CAN devices. See the address. Each node have different addresses and their binary values 0000001. Here assuming all 3, see the bus is ideal and begin transmitting at the same time. This is how the arbitration works out. All 3 devices will drive the bus to a dominant state for the start of frame, and the 2 most significant bits of each message identifier. Each device will monitor and determine success. When they write bit 8 of the message ID, the device writing message will notice but that the bus is in dominant state when it is tried to let to be recessive. See, but this bit will go out because here you have recessive. After that you have to compare, I mean the node device 2 and device 3 will go, and finally the device 2 11 10 9 8 7 6, the sixth bit here, it is recessive, but in device 2 it is dominant, I mean the ID 154 is dominant. So finally, see, the remaining devices will continue writing bits until the bit 5. Then the device writing message ID 187 will notice a collision and abort transmission. This leaves the device writing message ID, that is 154 is remaining, and it have the dominant. So finally, it will continue writing bits on the bus until complete or an error is detected. Notice that thus this arbitration method of arbitration will always cause the lowest numerical value message ID to have highest priority. The same thing is going to happen in 18-bit identifier also. This is 11-bit identifier. The same thing is going to happen in the 18-bit identifier also. I will explain all those things in my upcoming slides where 18-bit or 11-bit and everything. See, this is the typical CAN node. So you will have the microcontroller or else node. The node have CAN controller, and the CAN controller will do uh, transmit and receiver, transmitter and receiver. In between the CAN high and CAN low, you have CAN trans receiver. Finally, it will go to this CAN bus. This CAN bus is here, the CAN bus. Okay, already we know something about controller, CAN controller and everything. Here, the main thing is trans receiver. So CAN bus is a simple two-wire differential bus, serial bus, that is high and low. CAN high is one wire and CAN low is one wire. CAN bus is terminated on each side by a 120 ohm resistor. So the 120 ohms resistor is used to minimize the reflection reference and to reduce noise. So the 120 ohm resistor is not fixed. We can use 110 to 130, but standard is 120. See here the CAN trans receiver. What this CAN trans receiver will do. So the transceiver provides differential transmit capability to the bus and differential receive capability to the CAN controller. Transceiver provides an advanced interface between the protocol controller and the physical bus in a controller area network, that is CAN node. Typically, each node in a CAN system must have a device to convert the digital signals generated by the CAN controller to the signals suitable for transmission over the bus cabling, that is differential output. It also provides a buffer between the CAN controller and the high voltage spikes that can be generated on a CAN bus by outside sources, electromagnetic interference, electrical transients, etc. The CAN receiver is a device which detects the signal levels that are used in the CAN bus to the logical signal levels recognized by a microcontroller. You can see here the two states of CAN bus. Here recessive, that is logic 1, and dominant is logic 0. Dominant have the highest priority. See the CAN high and CAN low. This is driver logic. So you can see dominant voltage, recessive voltage, again dominant voltage. See, if it is 0 means both will be high. CAN high will be high, CAN low also. If it is 1 means the recessive voltage. I mean, if the difference, I mean, if the signal is dominant, if the bit is dominant means it will go up to 3.75 voltage here and it will come up to 1.25 something. If it is recessive means, and it will be, the difference will be 0, 2.5 volt, then the difference will be 0 based on the dominant or recessive. It may vary. Next one is CAN bus state, the same thing I mentioned there. So CAN low and CAN high. If it is 0, The same thing will happen here also. So, and we have types of CAN frames. We have data frame, remote frame, error frame, and overload frame. First one is data frame. The data frame is the only frame that for actual data transmission. So there are two types of message formats. One is base frame format with 11-bit identifier and extended frame format with 29-bit identifier. Yeah, data frame is composed of 7 different bit fields. That is start of frame, arbitration field, control field, data field, here arbitration field, control field, data field, CRC field, acknowledgement field, and end of frame. In this data frame, we have first one is arbitration field. The arbitration of the CAN message consists of, already I said that 11-bit or 29-bit identifier and a remote transmission RTR bit. The CAN arbitration, already I mentioned that, is called carrier sense multiple access with collision detection, and it assures that the highest priority message is broadcast. So message priority is determined by the numerical value of the identifier. Already we saw that in our before slides, is based on carrier sense multiple access, and with the lowest numerical value having the highest priority also. Non-destructive bitwise arbitration resolves these conflicts among competing transmitters. So here every node will have the startup frame as dominant bit, and based on the lowest level of priority only the node will wins is based on the arbitration field. Next one is control and data fields. Here control and data fields. So here the control and data fields frame consists of 6 bytes, both having 6 bytes. So maximum only lower 4 will be used. That indicates that the amount of data in a message. Since up to 8 bytes of data may be sent in this one message, the control field may take value ranging from 000000 to 000111, and the MSB data byte will be sent first with using of control and data field. So already I told that arbitration field, it consists of startup frame arbitration. The startup frame is always a single dominant bit to mark the beginning of a data frame. And the next one is arbitration. Here the two frame formats are there. One is standard format and extended format. In standard format we have 11-bit identifier. In extended format we have 11-bit, one SRR and one IDE, and another one is 18-bit identifier. The main difference is here 11-bit and here is 18-bit, and one more difference is that the identifier of the standard format corresponds to the base ID in the extended format. The RTR bit is the remote transmission request here and must be 0 in data frame. The SRR here bit is the substitute remote request and it is recessive. Recessive means it will be 1. The IDE field indicates whether the identifier is extended and should be recessive in the extended format. So the IDE field will be 0 in standard format and the IDE will be recessive in extended format. This is the main difference. So If you are going to attend an interview, sure, they will ask that what is the main difference between standard format and extended format. So the first difference is it is an 11-bit identifier and it is 29-bit identifier. Then the main difference is the IDE field. The IDE bit is recessive in extended format and it is 0, I mean dominant in standard format. Okay, you will have one question that if one node is from extended format and another node from standard format, both the maximum messages, first 11 messages are all are dominant. Even though all the messages in standard frame and extended frame are dominant, finally the standard frame only will win the arbitration because of it. It have uh, it have a it have dominant bit in the IDE and and the extended have recessive bit in the uh, recessive bit. The IDE bit is recessive in extended format. And you have here the control field. Already I told that the first bit is IDE bit for the standard format, but it is used to as reserved bit R1 in extended format. So R0 is common, is reserved bit. Here DLC data length code, these are the data length code, MSB to LSB. So can be from 000 to 1000. And this data length code, this data field have 0 to 8 bytes of data, maximum 64 bits or 8 bytes. Next one is CRC. CRC is cyclic redundancy check. So field, it contains the 16-bit CRC sequence and it is under CRC delimiter. The CRC delimiter is a single recessive bit. So the cyclic CRC are detected using a 15-bit CRC computed by the transmitter from the message content. Each receiver accepting the message and recalculates the CRC because transmitter have CRC and receiver also. The receiver will check whether the transmitter CRC and receiver CRC both are same. If it is not same, then the error will occur. Otherwise, nothing will, I mean, the error won't occur and it finally gives one acknowledgement. So the CRC and compares it against the transmitter. So receiver will have one value and transmitter node transmits one message, right? That they have one value, they will compare. So the two calculations cause an error flag to be set if there is any problem occurs. If the calculations are wrong means, and the error flag to be set. Then the frame checks that the error flag and error or detection by the receiver and the into the invalid delimiter also. Invalid CRC delimiter. And another one is we have acknowledgement field. It consists of here 2 bits. The first bit is acknowledgement bit. This bit is set to recessive by the transmitter but will be reset to dominant if the receiver acknowledges the data frame. Like this bit is set by the recessive to by the transmitter. While sending the data, the transmitter sets this bit to recessive. After the receiver acknowledges the data frame, then it will change that reset that recessive bit to dominant. The second bit is an acknowledged delimiter and it is again recessive. Another one is scan remote frame. It is used by a node to request other nodes to send certain type of messages. Like these fields are identical to those of the data frame, with the exceptions that the RTR bit in the arbitration field is recessive in the remote. So here we can see the remote frame. That is, here the main thing is, here we can say the remote frame has a node that requires data from another node on the network can request a transmission by sending a remote frame. For example, we can say that the microprocessor controlling the center locking on your car may need to know the state of the transmitter selector from the powertrain controller. A remote frame is the same as the data frame without the data field with the RTR bit recessive. So the main difference between the remote frame and the data frame is it's same like the data frame but without the data field. The data field here, see the data field, this won't be there in this remote frame, but with the RTR bit is recessive, the remote frame will be set. Next one is error frame. So the error frame, this frame consists of two fields. The first field is given by the superposition of error flags, that is 6 to 12 dominant or recessive bits contributed from different nodes. The second field is the error delimiter. So there are two types of error flags. One is active error flag or else passive error flags. 6 dominant bit transmitted by a node detecting an error on the network. This is called active error. 6 recessive bit transmitted by a node detecting on active error frame on the network. This is called error passive. See, this is error frame, superposition of error flags. So mostly you will get questions from this error frame, that is active error, passive error and a bus off. So active error occurs when transmit error count, that is TEC, start to increase from 0 to 127, that is 0 to 127 times. It is active error by increasing 8 counts for 16 times. For example, if I send a data, if there is any error, then the count will increases to 8. The same happens for 16 times, then the error active in a flow. If it ends with 16 times, 128 count starts, error passive will come into the picture. Next, if it exceeds the 128 count, then error passive will come. So here the error passive, once the counter completes 16th transition, that is 128 afters, the error goes to the error passive. So the error passive occurs when TEC starts from 128 to 255 by increasing 1 counts. So after that 128, it will go till 255. So once it completes 255 transition, then the error goes to bus off state. The entire node will be call off. So if it exceeds 255, then the node will be call off. And the bus off occurs under 3 conditions. First one is shorting the CAN lines. I already explained now, CAN high and CAN low. If you short the both lines, then the bus off will occur, ignoring the complete node. So if the message is not coming, or else if other nodes are trying to ignore one node, then it will happen, making error counters to reach minimum threshold for bus off conditions. So these are the chances that the bus off will occur. So in this bus off state, the CAN node will be removed from CAN network and now it will no longer available in CAN network to participate in any CAN activity. So it will completely removed from the node will be removed from the CAN network. It's not like removing the wires and all. The other nodes won't consider there is one node like that. If airbag node is there and it goes to bus off, means other node won't consider that there is one node like airbag, so they won't. It's like hide. Next one is overload frame. So consist of two bit fields, overload flag and overload delimiter. Three different overload conditions lead to the transmission of the overload frame. First one is internal condition of a receiver require a delay of the next data frame or remote frame. At least one node detects a dominant bit during intermission. A CAN node samples a dominant bit in the 8th bit. That is the last bit of an error delimiter or overload frame. So here this is the overload frame, and it consists of 6 dominant bits overload flag, and the overload delimiter consists of 8 recessive bits. And interframe space, this is not that much important, but you should know what are the frames. So data frame and remote frame are separated from preceding frames by the interframe space. Overload frames and error frames are not preceded by an interframe space. So this is so the intermission subfield consists of 3 recessive bits. During intermission, no node will allow to start transmission of the data frame or remote frame. So the period of bus ideal may be of arbitrary length. After an error passive node has transmitted a frame, it sends 8 recessive bits following intermission before starting to transmit a new message or recognizing the bus as ideal. So next one is message filtering. A node uses filter to decide whether to work on a specific message. Message filtering is applied to the whole identifier. A node can optionally implement mask registers that specify which bits in the identifier are examined with the filter. If mask registers are implemented, every bit of the mask registers must be programmable. So next one is bit stream encoding. The frame segments including start of frame, arbitration field, control field, data field and CRC sequence are encoded by bit stuffing. Whenever a transmitter detects 5 consecutive bits of identical value in the bit stream to be transmitted, it inserts a complementary bit in the actual transmitted in bit stream. The remaining bit field of the data frame or remote frame or CRC acknowledge field or end of frame are fixed form and not stuffed. The error frame and the overload frame are also fixed form and not encoded by the method of bit stuffing. The bit stuffing is a message is encoded using a non-return to zero method. In the non-return to zero encoding method, a bit is either recessive or dominant. So if 5 bits are in a same like 0 0 0 0 0, then the sixth bit it should be 1. If it is in 5, all the 5 bits are 1, then the sixth bit it should be 0. See, you can see the example of bit stuffing. See, first one is start of frame, then 0 0 0 0 0, 5 zeros and again 1 0 is there. But here you see 1 2 3 4, sorry, 1 2 3 4 5. After 5 consecutive dominants from start of frame and 4 bits, it automatically inserts one recessive bit. Then the data is flowing. See here also in data the same thing, 0 0 0 0 0, here 1. So this is bit stuffing. Next we have errors. In errors we have error handling, we have 5 types. First one is bit error. Bit error. A node that is sending a bit on a bus also monitors the bus. When a bit value monitored is different from the bit value being sent, the node interrupts and situation as an error. So if the one node is transmitting one data and the bit value monitored is different from the transmitted bit, then there will be an error. There are two exceptions to this rule. A node that sends a recessive bit during the stuffed bit stream and the arbitration field, or during the acknowledgement slots detects a dominant bit. A transmitter that sends a passive error flag detects a dominant bit. Next one is stuff error. 6 consecutive dominance or 6 consecutive recessive levels occurred in the messaging field. Already here we saw bit stuffing. It is bit stuffing if suppose the one is not inserted and it going like 0 0 0 or else 1 1 1 1 1, 6 consecutive zeros or 6 consecutive ones, it's related to stuff error. And CRC error. CRC error, already I mentioned that CRC sequences in the transmitted message consist of the result of the CRC calculation by the transmitter. So the transmitter only calculating the CRC in calculation. The receiver recalculates the CRC sequence using the same method but resulted in the different value. This is detected as a CRC error. Next one is form error. Detected when an fixed form bit field contains one or more illegal bits. And other thing is acknowledgement error. Detected whenever the transmitter does not monitor a dominant bit in the acknowledgement slot. Like if the transmitter transmits the data and the receiver receives the data, so the receiver should send the dominant bit to the transmitter. If the receiver or if the transmitter didn't get the dominant bit from the receiver side or else receiver node, it's like an acknowledgement error. And finally, error signaling. So a node that detects an error condition and signals the error by transmitting the error flag. So an error active node will transmit an error active flag. Already we have seen this. Then the fault confinement, that is error active, error passive and bus off. An error passive node will transmit a passive error flag. So finally the thing is fault confinement. So a node may be in one of the 3 states: error active, error passive and bus off. Already I have explained this one. When an error count is less than 128, then a node is in error active. When it equals or exceeds 128, not higher than 255, then it will be error passive. When an error counts equals or exceeds 256, the node will be in bus off state. The error active node will transmit an error active frame when detecting an error. The error passive node will transmit a passive frame when detecting an error. A bus off node is not allowed to take part in the bus communication. Finally, CAN message bit timing. The setting of a bit time in a CAN system must allow a bit sent out by the transmitter to reach the far end of the CAN bus and allow the receiver to send back acknowledgement and reach the transmitter. So this is called bit timing. The number of bits transmitted per seconds is defined as the nominal bit rate. So according to the CAN specification, the bit time is divided into 4 segments. Synchronization segment, the propagation time segment, the phase buffer segment 1 and phase buffer segment 2. Each segment consists of a specific programmable number of time quanta. So that is the length of the time quanta TQ, which is basic time unit of the bit time, is defined by the CAN controller. System clock frequencies and the baud rate prescaler. TQ equal to BRP, baud rate prescaler, divided by FSYS, that is frequencies. So the synchronization segment is the part of the bit time where the edges of the CAN bus levels are expected to occur. The distance between the edge that occurs outside the synchronization segment, see here. This is synchronization segment. And this time, see, time quanta, one time quanta. This is propagation. This is propagation time segment is intended to compensate for the physical delay times within the CAN network. Next one is the phase buffer segment. Phase buffer segment. See, this is phase buffer segment 1 and this is phase buffer segment 2. Surrounded by a sample point. Surrounded by a sample point. The resynchronization jump width defines how far a resynchronization may move to the sample point inside the limits defined by the phase buffer segment to compensate for edge phase errors. So this is the thing. So we should know that two types of errors, that two types of synchronization, that is odd synchronization and resynchronization. Yeah, hard synchronization is done once at the start of the frame. Inside the frame only resynchronization occurs. So you should know what is odd synchronization and what is resynchronization in CAN bit timings. After hard synchronization, the bit time is restarted when the end of synchronization segment, regardless of the edge phase error. Thus, hot synchronization forces the edge which has caused the hot synchronization to lie within the synchronization segment of the restarted bit time. Next one is bit resynchronization. Resynchronization leads to the shortening and lengthening of the bit time such that the position of the sample point is shifted with regard to the edge. So this is all about CAN. I just gave some brief explanations related to CAN. You should go through all these things what I gave, and I will upload the questions which are asked in some of the MNCs like Robert Bosch, Continental, KPIT. I will put some videos related to CAN important questions following to this video. You just go through all that videos also. It will be helpful who are looking for other automotive domains or else looking for other jobs. I'm having a lot of interview questions I ask in interviews. I'll update all those questions in my upcoming videos. So try to study all these things. Thank you.